Hello everyone, welcome. In this video we are going to go in depth of what minimum potential energy principle is about. We are going to visualize the equations with physical meaning that are involved in this principle. So let us first start with the statement of the principle. Of all the displacements which satisfy the boundary conditions of a structural system, those corresponding to stable equilibrium configurations make the total potential energy or relative minimum. So there are two terms that we have to first understand clearly to understand the minimum potential energy principle. That is stable equilibrium configuration, and the second one is potential energies that are involved in the structural system. So first let us talk about the three types of equilibrium states. First one is stable type of equilibrium, second one is unstable type of equilibrium, and third one is neutral type of equilibrium. Let us consider these are balls with some masses and they are constrained to move along these surfaces. Okay, and since in all three cases the downward weight of the balls are counteracted by the surfaces, they are in rest and they cannot move. That is why all three are equilibrium states. Now let us consider the potential energies of the balls. The potential energy that is involved in this system is gravitational potential energy, and gravitational potential energy tends to increase with increase in height or elevation, right? And also the law of nature is that force always acts in the direction of decreasing potential energy, right? So if I try to lift this ball, it will tend to fall down, right? Because it wants its potential energy to be as minimum as possible. So in this first case, if I try to displace ball anywhere along the surface, then it tries to fall back to its original state, that is at the bottom, right? So if I put this ball at this location, then it is not in equilibrium because it tends to slide down and be in motion. So since potential energy of this ball is increased, it tries to find its way down to lower potential energy. That is why it tries to be in motion, and that is why it is not in equilibrium state, right? And in second case, if I put this ball at this location, that is h below this ball, its potential energy decreases, and since its potential energy is lower, it does not try to get back to its higher potential energy state, that is its original configuration. So the ball tends to slide down indefinitely with no chance of coming back to the top. So again, why it slides down? Because the force that drives this ball is acting towards the direction of decreasing potential energy, that is downward. And in third case, if you put this ball at this location along this surface, then it is in equilibrium. The equilibrium is not disturbed, and unlike the first case, it does not return to its original configuration, right? So we are concerned about stable type of equilibrium because in fact all the structural systems that are in rest are in stable equilibrium state with minimum potential energy in them. So conclusion from this is that when potential energy is minimum, the body has stable equilibrium. Okay, so now let us try to understand the principle of minimum potential energy physically with an example. I have this spring that is attached to left on a rigid support, and on the right end a horizontal force F is acting to this direction, and this green dot here is called a node. Here this node is nothing but a representation of a point that is common to this spring and this force. Now we know that when force F acts at this point, then it tends to stretch the spring and this node displaces to the right. And we can easily determine how much distance this node gets displaced by using the force balance equation. That is, external force F is equal to the internal restoring force, that is K times X. K is the stiffness coefficient of this spring and x is the displacement of this node, that is F by K, right? So force balance method is quite easy, and you can easily find the displacement by just balancing the forces. Now let me tell you that we do not employ force balance equation in the context of minimum potential energy principle. A lot of students make this mistake that they try to find the logic behind the minimum potential energy with the help of this force balance equation. So we are not going to use this equation, and while studying minimum potential energy, you have to literally forget this force balance equation. We are not considering the forces. Rather, we have to visualize two potential energies that are involved in this system. First one is internal potential energy, that is the potential energy stored in the spring when it gets displaced. So when a spring is stressed by length x, then its potential energy increases by the amount half of kx squared. On the other hand, if spring is compressed by x, then in that case also the potential energy in the spring is going to get increased. So it doesn't depend whether the spring is compressed or stressed. As long as the original configuration of spring is disturbed, then its potential energy is always going to get increased, right? It does not depend upon the sign of x. This is quite easy, internal potential energy. The next is external potential energy, and this is often little hard for students to understand what exactly the external potential energy is. So I'll try to make it clear here. External potential energy is the energy that is possessed by the external force system. And when I say external force system, here F is only one force that is external to this system. So we consider F. And when we are talking about the minimum potential energy principle, and specifically this external potential energy, we have to forget all the system except the external forces. So we take this force alone. The reason I removed the spring on the left is because I do not want you to think that when this force displaces this node to the right, the spring is going to pull this force back to the left. You should not think that way, because as I already told you, we should not employ the force balance equation or force balance concept while talking about the minimum potential energy. We have to separately visualize external force system. Minimum potential energy is independent and fundamental in itself, so we do not employ force balancing equations, as I already told you. The only thing that connects the spring and external force system is this node. We have to remember that this node represents the right end of the spring and the point where force is acting. So the right end of the spring and this force cannot have separate displacements. We cannot avoid the compatibility condition, but we have to think that the spring is not pulling this force back to the original state when this node gets displaced. Okay. So what is external potential energy? As we have seen before, that ball with some gravitational potential energy, when get displaced along the height, its potential energy changed. But here we cannot see any force field like a gravitational force field. Rather we have this force, and we don't know where this force comes from, but we are at least sure that whatever physical cause that is resulting this pull or push at this point, that is this force, the potential energy of that physical system gets decreased when this node displaces to the right, because work is done along the direction of force, right? And if this node gets displaced to the left, then potential energy is going to get stored in that physical system that is causing this force. So when this node gets displaced to the right like this, then its potential energy is going to get lower. That is negative Fx is the decrease in potential energy in external force system. If you are not being able to visualize the external force system, or what is causing this force, where does this potential energy comes from, then I can with a little extension make you more clear. This is a pulley, and in this figure we can see that this force F is nothing but weight of this body, that is in gravitational field, right? So when this node gets displaced to the right, we know that the potential energy of this force system gets decreased, right? And if this node gets displaced to the left, then its potential energy is going to get higher, right? And if you assume that the potential energy of the external force system was 0 when spring was relaxed, that is, this node was at this location, then after displacement in positive x, the potential energy get reduced. That is why we put this negative sign. And another important thing that I want you to reconsider here is that many people get confused when they don't see half here in the front. The confusion is because they are trying to visualize the spring along with this external force system, and they consider that the spring should pull this force back to the left, and after x displacement, the external work done should be equal to the internal work done on the spring. That is wrong, because as I already told, we do not consider force balancing concept here. Minimum potential energy is not based on force balancing equation. It considers two potential energies as independent to each other. Okay, so now total potential energy in this system is equal to the sum of internal potential energy and external potential energy. UE is the internal potential energy possessed by this elastic system, and UF is the external potential energy of external force system. So UE is half kx squared and UF is negative of fx. Now, as I already told you, the physical system that are in rest are always at minimum potential energy. That is the state of stable equilibrium, right? So every physical system is in stable equilibrium, and for that they have minimum potential energy. And since the total potential energy that is denoted by here with capital letter pi is dependent on x, we can graphically visualize this total potential energy function. So I'm going to show you this in a graph. Notice that UF is a linear function that has a negative slope, and UE is a squared function, and the total energy pi is also a parabolic function here. So first let me draw this graph. This is external potential energy possessed by the external force system. The x-axis represents the displacement of the node, and y-axis represents the potential energy. When x increases, then the potential energy possessed by the external force system gets reduced, right? And when x decreases or displacement is to the left, then the potential energy is going to get increased. Next is the graph of potential energy possessed by the spring. This is a parabolic curve. It doesn't matter whether the displacement is on the right or left. The potential energy of the spring is always going to get increased, right? And the total potential energy is the sum of these two potential energies. So if I plot the graph of total potential energy, then we are going to get a parabolic curve like this. So as you notice that our physical system, that is spring force system, cannot remain at zero displacement. Why? Because at zero displacement there comes a force that drives the system towards lower potential energy. So as long as there is chance of getting to lower potential energy, our system cannot be at rest or in equilibrium, right? Our system is going to get displaced into a new configuration. That is, the node is displaced to this particular x where the total potential energy is minimum, right? So at this x, our system is in stable equilibrium state. I have presented same graph here with some labels. This is negative fx, this squared function is half kx square, and this is total potential energy pi. Now we know that our system will be in stable equilibrium configuration after this displacement where the potential energy is minimum. So now our concern is to how to denote this minimum potential energy mathematically. Mathematically we denote this point as like this: d pi is equal to 0. That is, infinitesimal change in pi, and since pi is a dependent variable which depends on x, the change in pi that is brought by infinitesimal change in x is 0 at this extreme point, right? If you have studied calculus, then it is not much of a big deal. So to find this x, we simply take derivative of pi with respect to our variable x. By doing so and solving this linear equation, we come to the same conclusion that we have derived from force balancing equation, right? The displacement is F over K. So the application of principle of minimum potential energy would be incomplete if I don't elaborate it with multinodal problems. So here we consider a spring with two nodes. At this node, F1 force is acting, and at this node, F2 force is acting. And the displacement of this first node is x1, and that of the second node is x2. The reason for assigning two nodes to this problem is because the displacement of these 2 points are independent to each other. They are going to take separate displacement, namely x1 and x2. So we have two nodal problem, and we have to find the displacement x1 and x2 when the external forces F1 and F2 act at these nodes, node 1 and node 2. So after the application of forces, these nodes get displaced. The total potential energy that is stored in the system after displacement is written like this. Remember that the potential energy of both internal and external systems were 0 when there is 0 displacement of these nodes. So here the total potential energy pi is dependent on two variables, x1 and x2. So if we try to plot the graph of total potential energy with respect to x1 and x2, then we get a 3D surface like this. Here this axis represents the displacement of this node, and this axis x2 represents the displacement of this node, and total potential energy that is given by this function is plotted along the vertical axis, and we get this surface which is more like a paraboloid. But the shape of this surface depends on number of constants that are K1 stiffness of this spring, K2 stiffness of this spring, F1 and F2. So it is not always a paraboloid, but one thing we have to consider here is that this surface has only one absolute minimum point. Okay, why? Because pi is a squared function, right? So that is why it has only one extreme value, and in this case extreme minimum point. So again, how do we represent this minimum total potential energy pi? Here is how. Mathematically we write like this: d pi is equal to 0. Just like in previous example, we do not write partial derivative symbol delta here. Rather we write d pi is equal to 0. Why? Because pi is a dependent variable that depends on x1 and x2. There are two independent variables, x1 and x2. So at minimum point, whatever infinitesimal displacement we are taking in x1 x2 plane, the corresponding infinitesimal change in pi is always 0, right? So this minimum point is not with respect to x1 or with respect to x2, but pi is minimum with respect to any of those independent variables. So how do we find the actual displacement x1 and x2 where the potential energy is minimum? This is the top view of the same graph. Here we are concerned with this point where the pi is minimum. So in order to get this coordinate x1 x2, we take the help of partial derivative. First we do partial derivative of pi with respect to x1. This will give us a linear equation where x1 is minimum for given x2, and we do partial differentiation of pi with respect to x2. This will give us another linear equation where x2 is minimum for given x1. So when we simultaneously solve these two linear equations, we get that particular x1 x2 where the pi is minimum with respect to both x1 and x2. So I've been saying that this differentiation will give linear equations. Why? Because pi is a square function, and partial differentiation of it will give us system of linear equations, right? So in this way we visualize that when F1 and F2 act on this spring system, then the spring will change its configuration such that the potential energy of that configuration would be minimum, and that will represent the actual stable equilibrium state of our system. So now I am going to conclude and generalize the principle. So now we know that using minimum potential energy principle, we can find out displacements at each degree of freedom of a structure for which the system attains stable equilibrium state. So at stable equilibrium state, the total potential energy has a minimum value, and to get the displacements at which the potential energy is minimum, we take the help of partial differentiation. And one thing you have to notice here is that xi, which represents a displacement at a node, where there is degree of freedom, there would be a displacement, and this displacement can be both translational or rotation too, right? When there is rotation, there are moments involved. So this partial differentiation equation will give us a system of linear equation, and if there are n degrees of freedom in a structural system, then we are going to get n system of linear equations. Then we can easily solve the linear equations, then get the displacements at each degree of freedom. Okay, so I hope you understood about minimum potential energy principle, and if you have any question regarding this topic, you can put it in comment box. I would be delighted to help you. And if you found this video useful, then please don't forget to subscribe the channel. And also let me tell you this, minimum potential energy principle is one of the most powerful tool that is used in finite element method to generate linear system of equations or to generate stiffness matrices that we will be seeing in the upcoming future videos. So until then, have a good time. Bye.